Welcome to our Quantum Deep Dive.
Hello.
Today we're embarking on a pretty fascinating journey, I think. We're looking at the intersection of two really cutting-edge fields, quantum computing and natural language processing, or NLP.
That's right.
And we're drawing insights from the detailed work of Jorgo Schneppat to kind of get a handle on the potential here.
Yeah, his work on quantum NLP really lays things out. It explores how these, frankly, bizarre rules of the quantum world could unlock totally new levels of intelligence in how computers understand and, process human language.
It sounds almost like science fiction.
It does a bit, but what's great about Schneppat's approach is that he outlines not just the possibilities, but also the fundamental principles that make it all conceivable.
Okay, so what's our mission today? We want to unpack why quantum computing might even be needed for NLP.
Right. What's the problem we're trying to solve?
Exactly. And then what core quantum mechanics principles make this possible? And finally, we'll dive into some really mind-bending applications, things like understanding emotions, maybe even better translation.
Sounds like a plan.
Okay, so before we jump into the quantum weirdness, let's set the stage. NLP. Natural language processing. It's huge in AI right now. Can you give us a quick refresher?
Sure. So NLP is basically the field trying to get computers to understand, interpret, and even generate human language.
Like talking to your phone or translation apps.
Exactly. Machine translation, chatbots, sentiment analysis, figuring out if a review is positive or negative, text classification. It's really central to modern AI.
And we've seen incredible progress, right, with deep learning models like GPT and BERT. They seem pretty powerful already.
Oh, absolutely. The progress has been stunning. These models can generate incredibly human-like text.
So why quantum then? If classical is so good, what are the limitations? What's the why here?
That's the crucial question. Despite these amazing advances, classical NLP methods are hitting some walls. Schneppat points out three key challenges.
Okay.
First, the sheer scale of data and computation needed. These big transformer models, they need absolutely colossal amounts of data to train. And the processing power required is just enormous.
Yeah, the energy consumption alone is a major topic.
It really is. Second, there's the issue of semantic depth. Classical algorithms, they struggle to efficiently grasp really deep semantic relationships and context. They're great at surface patterns, but true understanding, that's harder.
So nuance is tricky for them.
Very tricky. And third, related to the first point, is scalability and, again, energy consumption. Training and just running these massive language models is incredibly resource intensive. There are practical limits.
Okay, so data, depth, and resources. How does quantum computing propose to help with that?
Well, quantum computing offers a fundamentally different way to compute. It uses quantum mechanics, superposition, entanglement to perform calculations that are just, too slow or even impossible for classical computers.
How so?
Think about superposition. A quantum bit, a qubit, can be 0 and 1 at the same time. This allows for a kind of massive parallel computation.
Ah, so you could explore many possibilities simultaneously.
Precisely. This could potentially lead to dramatic speed-ups for complex NLP tasks.
And Schneppat mentions the quantum Fourier transform, the QFT, as an example.
Yes, and that's a big one. The QFT offers an exponential speed advantage over its classical counterpart for certain problems. That's not just faster, it's a different class of computation. It really hints at a fundamental shift in how we could approach language processing.
All right, to really get quantum NLP, we need to touch on those core quantum principles you mentioned. Superposition, entanglement, quantum interference. Can you break those down a bit?
Absolutely. These are really the building blocks. So first, superposition. Like I mentioned, a classical bit is 0 or 1. A qubit, it can be in a combination of both.
The alpha and beta states.
Exactly. Sierra wrangle, alpha 0 wrangle plus beta 1 wrangle. Alpha and beta are complex numbers. They tell you the probability of finding 0 or 1 when you measure it. But before measurement, it's in this combined state. This allows for that parallel processing we talked about.
Okay, so one qubit holds more information, in a way.
In a probabilistic sense, yes.
Correct.
Then there's Verschränkung or entanglement. This is maybe the weirdest one.
I've heard about this. Spooky action at a distance.
Kind of. It's a deep connection between two or more qubits. Their fates are linked instantly, no matter how far apart they are. Measuring one tells you something about the other immediately.
Wow. How does that help with language?
Well, imagine representing words or concepts as entangled qubits. You could potentially model very complex, long-range dependencies in text in a way that's just not feasible classically, like how a word early in a paragraph influences one much later.
Okay, that's powerful. And the third one, interference.
Right, quantum interference. Think of waves interfering. Quantum states have probability amplitudes, which are like waves. They can add up constructive interference or cancel each other out, destructive interference.
And how is that useful?
Quantum algorithms cleverly use interference to boost the probabilities of the correct answers and cancel out the wrong ones. It makes finding the right solution much more efficient for certain problems, like searching.
So these principles, superposition, entanglement, interference, they're the magic behind quantum computers. How do the machines themselves work? Qubits, algorithms, gates.
So qubits are the basic unit, like classical bits, but quantum. They exist in this complex space called a Hilbert space. Quantum algorithms are sequences of operations designed to exploit these quantum effects for speedups.
Like the one Snepat mentions, Grover's, Shor's.
Exactly. Grover's algorithm gives a quadratic speedup for searching unsorted databases. Think finding a specific piece of information in a massive text corpus much faster.
Okay, that sounds useful for NLP.
Definitely. Shor's algorithm is famous for breaking classical encryption, which is a whole other topic. But for NLP, things like the variational quantum eigensolver, or VQE, are really important. They're used for optimization problems, which pop up all over machine learning, including NLP.
And how do you actually do things to the qubits? How do you run these algorithms?
Through quantum gates. These are like the logic gates in your computer chip, but they perform quantum operations, unitary transformations on the qubits.
Examples.
The Hadamard gate, H gate, is fundamental. It puts a qubit into an equal superposition of 0 and 1. The CNOT gate, controlled not T, is crucial for creating entanglement between two qubits. You build algorithms by combining these gates.
Okay, let's tie this back directly to NLP. How do these quantum capabilities translate into real advantages for processing human language, according to the essay?
Snippet really focuses on three key potential benefits. First, that exponential parallelization we discussed. Quantum computers could potentially analyze vast amounts of text data much more efficiently than classical ones.
Handling the sheer volume.
Precisely. Second, more efficient semantic modeling. Because of superposition and entanglement, quantum systems might be able to model those deeper, more nuanced semantic relationships between words and concepts.
Like capturing ambiguity better.
Yes, or understanding context in a more holistic way. Maybe using entangled states to represent words within their specific context, like p-psi wrangle, semi-alpha, y-wrangle, sarangle, linking word-wang wrangle to context sarangle.
That sounds much richer than a simple vector.
It could be. And third, optimization of NLP models. Quantum algorithms like VQE or QAOA, Quantum Approximate Optimization Algorithm, could potentially find better parameters for complex NLP models or train them more efficiently.
All right, let's get concrete. Word embeddings are foundational in classical NLP, representing words as vectors. How does quantum word embeddings change the game?
So classical embeddings like word2vec or glove give you a fixed vector for each word. Math, B, fo, W1, W2, Wn. They're great for measuring similarity using things like cosine distance.
But they're static, right? Bank is always the same vector, whether it's a riverbank or a financial bank.
Exactly, that's the limitation. Quantum word embeddings propose representing words as quantum states, maybe even entangled states, in a Hilbert space. So a word like bank could exist as a superposition of its different meanings. Psi-wrangle, sumi-alpha, I-wrangle.
So the context could then select the right meaning.
Potentially, yes. Or the entanglement could directly link the word to its context, making the representation dynamic. It's a very different picture.
That is a shift. How does this then improve something like quantum semantic similarity, measuring how alike words are?
Well, if words are quantum states, their similarity isn't just a geometric distance. It's calculated using the overlap between these states, Langle with 2, and crucially, quantum interference can play a role here.
Interference, how?
The different components of the word meanings could interfere, allowing for a much finer-grained distinction based on context. Plus, you could potentially use Grover's algorithm to search for semantically similar words much faster, O-root N instead of O-N.
Faster and potentially more accurate. What about sentiment? Quantum sentiment analysis. Can quantum states really capture emotions?
It sounds strange, but potentially yes. Instead of just classifying text as positive, negative, or neutral, you could represent the sentiment as a quantum state. Pautsant wrangle plus beta text negative wrangle plus gamma text neutral wrangle.
So it could capture ambiguity like a sarcastic comment that's both positive and negative.
Exactly. Superposition is perfect for modeling that kind of ambiguity. Early work using things like quantum support vector machines or QSVMs is already exploring this and showing some promise.
Okay, let's push into even more complex areas. Text classification, sorting emails into spam, not spam, news articles by topic. How could quantum help there?
Classical methods like naive Bayes or SVMs, even deep learning, can struggle with the sheer number of features in text data, the high dimensionality, and capturing really complex context.
Right.
Quantum text classification could represent an entire document as a single quantum state, maybe Taizai D wrangle, so Sunny-Offy Y wrangle. Superposition and entanglement could then allow for much more efficient processing of this high-dimensional data, potentially capturing context better and scaling more effectively.
Interesting. What about sequence modeling? Things like speech recognition, machine translation, they rely heavily on understanding sequences, LSTMs, transformers.
Yeah, those are the workhorses now. Quantum mechanics offers ways to make sequence modeling potentially more efficient through parallel processing. A whole sentence could perhaps be represented as a single quantum superposition, CC-psi alpha wrangle.
Allowing you to process all words and their contexts simultaneously.
That's the idea.
Yeah.
And entanglement could be particularly powerful for capturing those tricky long-range dependencies in sequences, something classical models still struggle with.
And topic modeling. Finding hidden themes in large document collections.
Classical methods like LDA, latent Dirichlet allocation, can be computationally very expensive. Quantum approaches, leveraging interference, could potentially consider multiple semantic meanings of words simultaneously.
So a word like state could mean a political state or a state of being, and interference helps find the right topic.
Exactly. It could amplify the probability amplitudes corresponding to the relevant topics, leading to potentially more precise topic models, maybe even needing less data.
Okay, let's shift to communication. Machine translation.
Yeah.
Huge area. What are the quantum prospects there?
This is a really interesting one. Current NMT models, like Google Translate, are amazing, but still face challenges. Deep context, subtle ambiguities, and again, the computational cost.
So how does quantum tackle this?
Several ways. Superposition could allow the parallel evaluation of many different translation possibilities at once.
Instead of trying them one by one.
Right. Entanglement could be used to create richer links between words in the source language and their potential translations and context, maybe like PI tick sets, sumai, alpha vowels wrangle, he wrangle, and then quantum interference could help select the best overall translation by amplifying the probability of the most coherent output. Maybe even Grovers could speed up the search.
Fascinating. And named entity recognition. NER, finding people, places, organizations in text.
Classical NER often struggles with ambiguity. Is Washington the state, the person, or the DC? Quantum superposition could allow a word like Washington to simultaneously exist in the categories person, place, organization, represented as pletext, entetext, person wrangle plus beta text organization or plus gamma text organization wrangle. The context, potentially modeled with entanglement, would then help resolve the ambiguity.
So the quantum state itself holds the possibility.
Exactly. Entanglement could explicitly link an entity to its context, like associating Einstein with person and NASA with organization in a shared state.
Moving towards generation and retrieval. Quantum text summarization. Making long text short efficiently.
Yeah, summarization is key. Quantum mechanics could help here too. Superposition might allow for the parallel analysis of different sentence combinations or text structures to find the best summary, maybe represented as psi text, Zusum, and Fasurangle, where psi are candidate summaries.
And interference could help prune bad summaries.
Right. Interference could suppress redundant or irrelevant sentences. Entanglement could help ensure the summary maintains the thematic coherence of the original text.
What about language modeling itself? The core of models like GPT.
Classical models like GPT and BERT are incredibly powerful, but, as we said, computationally intense and can struggle with very long-range context. Quantum language models might use superposition for parallel word prediction, exploring multiple likely next words at once.
And entanglement for context.
Exactly. Potentially leading to better context handling over longer distances. Some researchers are even exploring quantum transformers, hoping to make these powerful architectures more efficient using quantum principles. Reducing those huge compute needs would be a massive win.
Finally, information retrieval. Searching vast databases for relevant documents.
Classical search struggles with scale and true semantic understanding, finding documents about a concept, not just keywords. Quantum methods could use superposition to represent the query and search across countless documents in parallel, maybe piece and phrase wrangle, LPT wrangle.
Grover's algorithm again for speed?
Yes, Grover's promises that O root N speed up for the search itself. Plus, quantum interference might enable much better relevance assessment, going beyond keyword matching to genuine conceptual similarity.
Wow. The essay also touches on even more advanced things like quantum question answering, coreference resolution, text generation, knowledge graph construction. The potential seems enormous. Okay, this all sounds incredibly powerful, almost revolutionary. But let's get real. What are the major roadblocks? Why isn't quantum NLP everywhere already?
Yeah, it's crucial to be realistic. There are very significant technical challenges. Schneppat highlights several. First and foremost, scalability and hardware limitations.
The computers just aren't big or good enough yet.
Pretty much. We don't have enough high-quality, stable qubits, quantum bits, and the ones we do have are noisy. They suffer from errors due to interaction with the environment. This limits the complexity of algorithms we can run reliably.
So error correction is a huge field in itself.
A massive one.
What?
Second, there are algorithmic challenges. Translating these theoretical quantum advantages into practical algorithms that actually outperform highly optimized classical NLP methods is really hard.
It's not always a clear win.
Not yet, not for many tasks. Many current ideas are still experimental, or they rely on hybrid classical quantum approaches, using quantum for specific subtasks. Getting a purely quantum speed-up for complex NLP is tough.
And the cost.
Right. Third is computational cost and training. Even simulating these quantum algorithms classically to develop them is incredibly resource-intensive, and training large-scale quantum models will require new techniques we're still figuring out.
Okay, so big challenges. But assuming we overcome them or find clever workarounds, where do you see quantum NLP making the biggest impact down the line?
The potential is definitely there, across many sectors. Schneppat mentions a few key areas. In the economy and finance, think faster analysis of market news for algorithmic trading, or much deeper risk assessment from reports.
Processing information faster and with more understanding.
Exactly. In science and research, imagine automatically analyzing mountains of scientific papers to accelerate drug discovery, or making sense of huge data sets from experiments.
That could really speed up innovation.
Absolutely. And in industry and production, perhaps processing complex technical manuals instantly for fault diagnosis, or optimizing global supply chains by understanding logistics reports in real time.
This kind of power also brings up ethical questions, doesn't it? Privacy, misuse.
Oh, definitely. That's a critical aspect. The ability to analyze vast amounts of text data so quickly could pose serious privacy risks if not managed carefully.
And concerns about misuse.
Yes, things like generating highly convincing fake news at scale or enabling more sophisticated forms of surveillance. It underscores the need for strong ethical guidelines and robust security. And crucially, the development of quantum-resistant cryptography, because powerful quantum computers could eventually break the encryption that protects our data today.
A double-edged sword, then. So, timeline-wise, when might we see quantum NLP become truly practical? Are we talking next year, next decade, next century?
Schneppat suggests a phased outlook, which seems sensible. In the short term, maybe the next, say, 0 to 5 years. The focus is really on improving the hardware, getting more and better qubits, and developing these initial hybrid quantum classical models for specific niche problems.
Testing the waters.
Exactly. In the midterm, perhaps 5 to 10 years, we might start seeing more specialized industrial applications where quantum offers a distinct advantage as hardware continues to improve.
And long-term.
Long-term, thinking 10 years or more out, that's where we might see the emergence of fully quantum NLP systems that genuinely surpass classical methods on a wider range of tasks, leading to more widespread adoption. But that depends heavily on sustained progress in hardware and algorithms.
What are the key breakthroughs we need to get there?
Better quantum error correction is absolutely fundamental. We need fault-tolerant quantum computers.
Mm-hmm.
We also need genuinely new algorithms specifically designed to harness quantum phenomena for NLP tasks, not just quantum versions of classical ideas. And finally, better integration with advanced classical machine learning, figuring out how quantum and classical systems can work together effectively.
Well, that was a truly mind-bending exploration of quantum NLP. It's clear that while the path forward has challenges, the potential impact on how machines understand and interact with human language is just immense.
It really is. The insights from Jirgo Schneppat's work paint a picture of a future where quantum mechanics could bring unprecedented efficiency, yes, but also maybe unprecedented depth to language processing.
It definitely leaves you thinking.
It does, and it raises that important question for all of you listening. If this technology matures, what kinds of linguistic tasks, maybe things we currently consider impossible for machines, will suddenly become achievable?
A future to ponder indeed. If you want to dive even deeper into this fascinating topic yourself, you can explore the work further at sneppat.de.
Definitely worth checking out.
Thank you so much for joining us for this quantum deep dive. We'll catch you next time.
Thanks for listening.